Hello friends, this is Jagdish, Perk Associate. Today's topic is gate. So in today's video, I will be explaining a strength of materials numerical problem which was appeared in the gate paper 2006. So before going to this video, please press the subscribe button of our channel, The Mechanical Engineers Theme, and also click the bell icon so that you will get the notifications for new videos. So let's begin. First I will read the question. A steel bar of 40 mm into 40 mm square cross section is subjected to an axial compressive load of 200 kN. If the length of the bar is 2 meter and E is equal to 200 gigapascal, the elongation of the bar will be A 1.25 mm, B 2.70 mm, C 4.05 mm, D 5.40 mm. Now I will analyze the question. There is a steel bar and the cross section of the steel bar is square. In simple words, there is a square steel bar. So you can see here the picture of the square steel bar. So the length of the steel bar is 2 meter. The Young's modulus of the steel bar is 200 gigapascal, and the cross section area of the square steel bar is 40 mm into 40 mm. Now a load of 200 kN is applied on the steel bar, and this load is a compressive load. Therefore, the length of the steel bar will be decreased and the cross-section area of the square steel bar will be changed. So in this question, we have to find the value of decreased length of the steel bar due to the application of 200 kN. Okay. Now I will list out the given conditions. Area of the square bar, which is 40 mm into 40 mm, and it is taken as A. Axial compressive load, which is 200 kN, and it is taken as F. Length of the square bar is 2 meter and it is taken as L, and the Young's modulus of square bar is 200 gigapascal and it is taken as E. So by using these four conditions, we are going to find the elongation of the bar or the deformation induced in the bar. Now I will move to the solving technique. Elongation of the square bar, which is taken as DL. And the universal formula for elongation of uniform bar is given by dl is equal to FL by AE, where F is force applied, L is length of the bar, A is area of the bar, E is Young's modulus. So in this formula we know the values of F, L, A and E. So just substitute the values. By substituting those values, we get dl is equal to 200 kN into 2 meter divided by 40 mm into 40 mm into 200 gigapascal. We know that kilonewton is 10 power 3 Newton and 1 meter is 10 power 3 mm and gigapascal is 10 power 3 Newton per mm square. Therefore, 200 kilonewton will be rewritten as 200 into 10 power 3 Newton, and 2 meter will be rewritten as 2 into 10 power 3 mm, and 200 gigapascal will be rewritten as 200 into 10 power 3 Newton per mm square. Therefore, dl is equal to 200 into 10 power 3 Newton into 2 into 10 power 3 mm divided by 40 mm into 40 mm into 200 into 10 power 3 Newton per mm square. So in this RHS, I am going to split the numerical terms and S units. Therefore, dl is equal to 200 into 10 power 3 into 2 into 10 power 3 divided by 40 into 40 into 200 into 10 power 3 into Newton into mm divided by mm into Newton per mm square. So here 200 into 10 power 3 into 2 into 10 power 3 is 400 into 10 power 6, and 40 into 40 into 200 into 10 power 3 is 320 into 10 power 6, and mm into mm is mm square. So dl is equal to 400 into 10 power 6 divided by 320 into 10 power 6 into Newton into mm divided by mm square into Newton per mm square. In this RHS, mm square and mm square gets cancelled, and 400 into 10 power 6 divided by 320 into 10 power 6 is 1.25. Therefore, dl is equal to 1.25 into Newton into mm divided by Newton. So in this RHS, Newton gets cancelled. Therefore, dl is equal to 1.25 mm. So the elongation or deformation induced in the steel bar is 1.25 mm. which is the decreased length of the steel bar is 1.25 mm. So the solution is A is the right answer. You can see here among these four options, A holds the value of 1.25 mm. So this brings an end to the explanation part of this problem. I hope you all would have understood. If any doubts are there, please do comment in comment box, and remember to like, share and comment on our videos. Thank you friends.